So now you can see that this is what dv by dot ds is written as the total derivative of the potential. So now it depends upon 1 and 2. So this is potential v1 minus v2, because it is going to be v2 minus v1, but because of this negative term it's going to be v1 minus v2. So now the work done is now here is going out to be, first we know that this work done is going to be the change in kinetic energy, and the second is the work done here in this case is the change in the potential energy. Okay, so if you combine these two, what you're going to get is equate these two. So you're going to get T1 plus V1 plus T2 plus V2, and similarly is going to be constant. So this is the conservation of energy theorem, which says that if the forces acting on a particle are conservative, so that has to be conservative. Whether the force is conservative, non-conservative, it is going to the kind of change in the kinetic energy, and this is going to be the if it is conservative, it is going to be change in the potential energy. So the force acting on the particle are conservative, then the total energy of the particle is going to be conserved. That is the kinetic energy plus potential energy. That is going to be the mechanical energy of the particle. It is going to be conserved. This is the energy conservation theorem. So this is in this system, what I have learned is when we're dealing with a particle of certain mass m, if you apply a force on the system, what factors you're going to have? First thing you're going to have is r, and then from there you're going to have v, and then from there you're going to have p, and then you have F external is dp by dt, that is going to be p dot. From there you get the conservation of linear momentum, and this was the first part. And the second part, when you apply the torque, and then you're going to have the angular momentum, and then this torque and angular momentum is going to related with dl by dt, and this is going to be L dot. So when n effective is going to be 0, so L is conserved quantity, conservation of the angular momentum. Then we come to the energy conservation, that is T1 plus V1 is going to be constant. So when I have a particle or an object of mass m, a force is acting, whether it is going to translation motion or when it is doing a rotational motion of this object. So you're going to have the conservation of linear momentum, conservation of angular momentum, but the total energy is going to be conserved. We learn about the conservative forces, and that is path independent. The work done closed curve is 0, and then this is very important part, that is this, if the force is conservative, that you always remember that it can be written in terms of the gradient of the potential. Okay, so this is very important. Now let's move to from one particle system to a system of particles. So how the dynamics changes. Okay, so if I have a system consists of a number of particles, then we have the equation of motion. Earlier, if you see that we don't have this equation Fij, this is internal forces, motions are not there. We have external forces applying on each and every particle or of ith particle, and this is Fij. This is this represent the internal forces between if each particle of the constituent is applying on each other. Okay, so this is the total force acting Fe and Fij sum over j, whatever the number j is going to from the n1 to n particle, what is the number of the particle inside the system is going to be d dt of this linear momentum of the system, that is p dot. This is going to be the total linear momentum of the whole system. Okay, which consists of the n number of particles. And if you apply the Newton's third law here, that's like if a particle if one particle apply a force on the other particle, this is equally applying a force onto each other. So Fij is going to be minus Fji in this force, which is the internal force, and then Fii is 0, because a particle applying a force into internal forces is getting cancelled with each other. So summing all the forces, external forces acting on the particle, ith particle, so what we have is, because this is going to cancel each other, equal and opposite forces, and for self interaction of the particle is going to be 0, Fi is going to be 0. So this is this Fi is going to be this sum over, because this that has to be sum over this this I, because summing over all the particles. So this is here also, you can write this is summing over I. So this is the momentum, mass of the particle, each particle, and this is because P is basically m times v. So v is basically d2r by dt square. So what you write is d2r by dt square is the position vector of our ith particle, position vector of the jth particle. Similarly, I have all the position vector of all the constituent particles, sum over all the things, and then what you have, the total force which is acting on this particle is going to be this mass times d2ri upon dt square. So this is what we have from the Newton's third law perspective, that the differential equations, second order differential equations. But when we're dealing with a system which consists of the number of particles, we define a center of mass of the system. So that is defined in terms of, that is R, the position vector of the center of mass. If the center of mass of this object is exists at this position, this is going to be sum over mi/ri divided by the total mass of the system, where this quantity is the total mass of the system. And if you see this going to this relation, that is sum over multiplied by this, if you do the cross product, this is mri minus r over mi is going to be 0. So this particular equation we are going to use later on in this lecture. So moving further, so what we have is the force which is acting. This equation state that the center of mass moves as if the entire external force act on the total mass of the system, because the total force, if that sum over j or I, that is Fij, that was not going to contribute. So I have the external force acting on the system, that is mi, and this is d2r upon dt square. So this sum over total mass, this is I, is going to be the total mass, and so you can write it here as I, this is summing over I, total mass, and I have d2r upon dt square. So this is the equation which is telling you that if the total external force is acting on the center where you suppose that the total mass of the system is being concentrated, or this virtual position. And from there, that same equation, as I told you, that the linear momentum of the system, so from, if you define R is sum over mi ri, sum over I divided by sum over I or mi, from here you get this relation. So from there we can define the total linear momentum, that is P is going to be mr dri upon dt, because this is going to give me, this has to be I, and this is m, and this is dr by dt effective is going to be capital R. This is the position vector of the center of mass of the system. So from this equation, it follows that if the external force is going to be 0, as we did in like in one particle system, is going to be 0, then this m dr d2r upon dt square is going to be 0. So this is the total momentum of the system is going to be a constant quantity. This is conservation of the total linear momentum of the system of particle. Okay, this is exactly same as we talk about this one system particle. This is a one particle system, and now we have a system consisting of n number of particles. So we talk in terms of the center of mass, such that the total force is acting, external force, effective force is acting on the point whose position vector is capital R, where the center of mass is situated, and then that contributes to the total linear momentum of the system. Now with this linear equation, we move to the angular momentum. So if I have a torque which is defined as this torque N, the bold face is going to represent the vector of this, because all these are bold faces, and I don't need to write this vector notation on each and every time. So this is all bold. So wherever you have a bold there, this is going to represent a vector quantity. So if I have a torque defined as this is R is the position vector of each and every constituent particle of the system. So this is going to be have like if you have many particles consisting of the system, this is R ith particle, this is R jth particle. So that's why if I have n number of particle, I is going to 1 to n, this is R cross F, so force acting on this ith particle, jth particle, and all these. So because this F consists of, you know, this is going to be the external force, as well as this plus some external force, and then internal forces, the particle interacting with each other. This particle is applying force on this, applying force on this is applying force on this particle, this is applying for this. These kind of forces are being taken care by Fij. So moving further, we have this look this, we're going to deal with this RIFIJ part. This is RIFIJ part is I can write this is half, because you see that why it is half times this plus this, because when you consider there's a double counting, because the one particle is this particle is applying a force on this particle. So this is F, like say this is F1 2, this one is applying on this 2, and this 2 is applying on this one particles. When you are summing over this, so when you're summing keeping I constant, okay, if you put F1 and then vary the 2j from 1 to n, so this is going to be F1 2, F1 1 plus F1 3 plus F1 4. So I'm keeping I constant and the force acting on this first particle with all the other particle, and then I am keeping this j constant, this and this F1 1 plus j constant 1, F3 1 plus F3 or F4 1. So I'm keeping the j constant 1 1 1 and varying the I. So there is a double counting. That's why the average force we talk about this is half this R cross Fij and R cross Fji. So this we can safely write, this is Ri minus Rj times the Fji. So this Ri minus Rj is the Rij vector, because if you see that if I have ith particle, so this is Ri, and if I have the jth particle, this is going to have Rj position vector. So this Ri minus Rj, so this is Ri minus Rj, this is going to be Rij. Okay, so this is going to be 0, because we know is already, because since the definition of Fij is parallel to Rij, this is cross product, so this is going to be Rf sine theta. So if they are parallel, the sine 0 is going to be 0 in this case. So the internal forces between two particles, in addition to being equal and opposite, also lie along the line joining the particles. So that's why it's a condition known as the strong law of action of reaction. That's why this is going to be parallel, and that's going to be Fij is going to be minus Fji. So this is the Newton's third law. So overall, when we're dealing with the system of particles, the torque, effective torque acting on the external torque acting on the particle system is Ri cross the external force which is acting on the system. So this naturally, because R cross F is basically the total angular momentum of the system. That is, this L is basically the total angular momentum of the system, which is given in terms of the Ri and Pi, because this Li of you say that this is sum over I Li. This is what? This is basically what is the position vector of ith particle and what is the position vector of or the corresponding momentum of that particle. That summing over is giving me all these, say this is R1 cross P1 plus R2 cross P2 plus R3 cross P3, and all these are going to give me this L1. This is going to give me L1, this is going to give me L2, and this is going to give me L3, and then vector summing all these L1, L2, L3 is going to give me the total angular momentum of the system of the particle. Okay. Now this is one important thing when the system is rotating. So it can have center of mass part as well as something is rotating about the center of mass. So let's try to understand it, that we have a system of particles whose center of mass is at this position. This is R is the position vector of the center of mass, and I have, for example, Ri is the ith position vector of this particle. And from the center of mass point of view, if I fix this axis over here, so if we can define the position vector of this ith particle with respect to this center of mass, so that is going to be Ri prime. So from here you can write this vector notation, that is Ri is going to be sum of this R and this Ri prime, and then similarly for the velocity, V is V prime plus V. V is the velocity of the center of mass, that is dr by dt, and V prime is velocity of this ith particle. This is dri by dt, that is the velocity of this particle with respect to the center of mass, not with respect to this position O. Okay, so there is different, that Vi prime is the velocity of the ith particle when you are standing here at the center of mass and trying to see that what is the velocity of that particle. So it follows from that, if you write the total angular momentum is R cross P, so I can write R is P is m times V, and this is R cross mv, and write this. I'm going to use this R relation, these two velocity and position vector relation here. This is mi, Ri, we are using Ri is Ri plus R, this relation, and this Vi prime plus V, this relation in place of this Vi. Okay. So now let us break it. So if you break this mi, you take mi Ri, and then you take the product of this V. So this is going to be R cross V, and you take the product with this V prime. So this is going to be the mi Ri V prime. Similarly, if you see this is mi Ri prime and take Vi prime, so this is going to be this thing, and then you go this to V. This is going to be mi Ri prime times V. So the important part here is let's do the sum of the last two terms, this one and this one. So mi Ri cross V and R cross Vi. Okay, so what if you open this, this is what I have, and this R is outside, and Vi prime is, this is dri by dt. I can take m inside, and this is d dt of Ri prime. Okay, this is going to be 0. Okay, because why this, the total is going to be 0, and why this is going to be 0? Because you know this mi Ri. So if you go from here, this is Ri prime is going to be Ri minus R. So if I multiply by R this, so I'm going to do mi Ri prime and mi Ri and mr. Okay, so this is going to be 0, because this is what this is effectively is going to give me the m, and this is sum over Ri is going to be this position vector of R, because you already know that you define this R is sum over mi Ri divided by sum over this is mi. So this is R times mi minus sum over mi Ri is going to be 0. So this is what contribute to a 0 of this position. So ultimately these two terms all together is going to be 0, and we are left with these two terms. So you can see that these two terms are very important terms. One is mi Ri cross V, and the second term is mi Ri cross Vi prime. The prime is there. Whenever you have the prime is there, that means you are looking the system with respect to the center of mass, not from this position. Okay, so that is this angular momentum, total angular momentum, consisting of two parts. One is, that is the angular momentum of the center of mass, and this is the angular momentum about the center of mass, that you are seeing something is moving around this. So this is basically, if you see that the total angular momentum of the system is equal to the angular momentum of the system concentrated in the center of mass, okay, r cross mv, plus the angular momentum of the motion around the center of mass, that is the spin angular momentum. So this part is basically the spin angular momentum. That is, the earth is spinning about its own axis, and this is orbital angular momentum. In terms of, we know that is orbital angular momentum, orbital angular momentum, like earth is rotating about the sun and the earth is spinning about its own axis. So this is about the center of mass rotation, and this is with respect to certain uh, reference point. Okay, so this is important, like that this was not there when you're dealing with a single particle of mass m. When you have a system of particle, then you have the total angular momentum is going to have the two component. One is the center of mass and counterpart, and then the total constituent particles are moving around the center of mass, that is the spin angular momentum. So as we did calculated this kinetic energy part in the translation motion for the single particle. If you look into here this system, that this T is sum over this mi times vi square, because vi correspond to the all those position vector of individual constituent particles. But that is vi is, if you remember, this is vi prime plus v, so square is there, so I can have this vi prime, there's dot product with this, and if I open this, we get v square, v dot v, and we got v prime square, and then the dot product of this v dot v prime and v prime dot v. So this is simple. This is half mv square, this v prime square, and this part is you can take this v, I think, common, because v dot v is there, v dot v is there. I can take v common, and this is d dt of mi ri prime, because this is vi prime is nothing but dri prime by dt. So this, in place of vr prime, I write d dt of ri prime, and this is going to be 0. We had already discussed it. So what we have is the two term. This is going to be the center of mass part, the kinetic energy of the center of mass, and this is the kinetic energy about the center of mass. So as the angular momentum is going to have the angular momentum of the center of mass and about the center of mass, the kinetic energy is also going to have the kinetic energy of the center of mass and kinetic energy about the center of mass. So moving further with the same concept of the work, so we define the work in case of a system of particles when a force is acting on this. So we have going from 1 to 2 and summing over all the constituent particles. This is Fi dot ds. So this F consists of the external force and all the internal forces between all those particles. Considering, if you remember, this total force is F external plus sum over ij. This is Fij, whatever it is. So you see we have two component forces. So this is not going to contribute, because from the strong third law, so Fij is equal to Fji. So again, the equation of motion can be used to reduce this integral, because if I have a surviving component is Fi dsi, so we write the second equation, m times acceleration dv by dt, and dsi is v times dt. So again, I can write this is dv by dt dot v, as I can write it is d dt of half v square. I can write it. So the same, with the same analogy, this is d dt of half mv square. And then, finally we already did this calculation, that is going to be the change in the kinetic energy. So here also the work done is going to be the change in the kinetic energy, and depending upon what is the kinetic energy at one position and kinetic energy in another position. And if the external force as well as the external forces are conservative, so this, as we know that this force, if the forces are conservative, that can be written in terms of the gradient of the scalar function, which is going to be the potential. So if this external internal forces are conservative, so this force I can write it as this is going to be the gradient of this negative of the potential. And then we know that this is this del v dot ds can be written as, we have already gone through this, that how to write this. So this is going to be the change in the potential, okay, v2 minus v2 minus v1, or v1 minus v2 with this negative sign. So again, what we have is the work done is the change in kinetic energy as well as is going to have the potential energy. But either here this delta I indicates that the derivatives are with respect to the components of Ri, because many constituent particles are there. So whether derivative is on the ith particle, for the kth particle, or the jth particle, that is what have to be careful about. So for internal forces, what we have, Fji is like minus delta ij, and that is going to be plus, because we know that this Fji is going to be F minus j. And Vij, so this is Vij is potential because of these two particle 1 and 2 through which the forces are acting, between which the forces are acting, and then Vij is depending upon Rij. So you see that this is the ith particle, this is the jth particle, and you have Ri, and then you have Rj here, and then you have Rij, that is Ri minus Rj is there. So this is depending upon Ri minus Rj, so that this Fgi n is equal to minus Fgi. So but these are basically automatically equal and opposite, because we had discussed it why it is there. They lie along the joining the particle. So this this potential is going to have certain this Rij with some scalar function f, and ultimately I can write this because we had discussed that why we have to divide with 2 to average out the double counting, that particle 1 is applying force on the 2, particle 2 is applying force on the particle number 1, and the corresponding displacement between these two. So if I write this in terms of the potential, that is minus delta I acting on the ith particle because the motion in the ith particle, and acting delta j because the motion in the jth particle. So what we have is this is you see that we had already discussed the delta I Vij is plus of this is going to be this is delta j, and so and ds my dj is going to be normally this is what is delta ri and delta j on the same concept that ri minus rj is delta rij. So this is going to be delta I Vij is going to be delta ij dsi and delta ij Vij. Okay, so then what I'm going to have is this with the half factor, this is going to be delta Rij, and now we reach to the same expression that delta V dot ds is going to be dv. Okay, so this is again going to give me the change in the potential. Okay, but there is a two potential. One is because of because of the external force which is applying, and one is coming because of the internal forces. Between forces are being cancelled with each other, but there is potential exists no potential, because the force is coming because of the gradient of the potential. Whether this force is going to be zero or not effectively, but potential is there, which is acting between the two particles 1, 2 and all the constituent particle. So from the potential point of view, this is when we're dealing with the constituent particle, then one part is the potential which corresponds to the external force, and the potential which is corresponding to the internal interaction, the self interaction of the particle inside the system. So from these considerations, it is clear that if the external and internal forces are both derivable from the potential, that is Fe or Fij is going to be minus delta Ij Vij derived from the potential. So it is possible to define a total potential energy which is V of the system such that the total energy is conserved. Okay, so again here we have T plus V is going to be a constant quantity. And I think this is all okay for this lecture. And from the next this is I think this is all okay for with the review of the Newtonian mechanics. Now from the next lecture I will start with uh, the prerequisite and to have to base to build the Lagrangian dynamics of the system. So I think if you have any queries and questions about whatever these two lectures have been covered, whatever have been covered within these two lectures, you can email me and then I'll try to answer your queries and questions. Have a nice day. Thank you.